Okay, welcome. Today we're very happy to have Dr. Dan Welling from University of Michigan. Dan is currently an assistant research scientist at the University of Michigan Department of Atmospheric, Oceanic, and Space Sciences. Dan received his PhD from the University of Michigan in 2009, and then did his postdoc at Los Alamos, not too far from here, down in New Mexico. And his research includes source and entry mechanism of plasma into the magnetosphere using multi-species MHD and also in situ measurement, the impact of ionosphere outflows on development of ring current. And at Michigan, he's now doing some groundbreaking simulations that couple ionosphere outflow to multi-fluid MHD, which I think is actually today he's going to talk about ion outflow and ring current. And also, I should mention, he was a founding member of the Space Weather Forecasting Technology startup company, which is no more, I guess?
No more, no. It didn't start up enough.
Okay.
Well, I think this needs to be a little louder. I'll shout until this turns on. Thank everybody for coming out today. It's actually a really good crowd, and it's amazing how many faces I recognize from the HAO area. It's really neat to be out here. So I want to especially thank Mike Wiltberger for inviting me out and giving me a chance today to talk about a topic that is very near and dear to my heart, which is the effects of ionospheric outflow on magnetospheric dynamics, and conversely and simultaneously, the effects of magnetospheric dynamics back on the acceleration and development of ionospheric outflows. Now, specifically today, I want to talk about how the ring current, which is the warm torus of plasma surrounding the Earth that intensifies during geomagnetic storms, can form a two-way feedback relationship, including mass and energy, with ionospheric outflow. So this is a paper excuse me, one thing with these mics, I can't avoid coughing into it. This is a paper I'm getting ready to submit to JGR with several co-authors, Alex Glosser from NASA Goddard, Vanya Jordanova from Los Alamos, Mike Lamone and Gabor Toth from University of Michigan, and I recently got help from Dan Weimer at Virginia Tech, and I think you'll be able to see these people's fingerprints all over this project. So before I dive right in, I did want to spend a little bit of time on the magnetosphere because I'm not sure what everyone's background is here, and it sounds like you guys are pretty spread out between the atmosphere and the sun and everything. So let's start with the magnetosphere. As you move out into space and you exit any region that you would recognize as the atmosphere, the important characteristic you see is the Earth's magnetic field. And this, if there's no external forces acting on it, is basically a dipole. If you continue to move away from the Earth, you see, of course, the solar wind, a tenuous, hot, supersonically flowing plasma that is carrying with it the sun's magnetic field out into interplanetary space. Now, when the solar wind encounters an obstacle like the magnetosphere, first it is shocked from supersonic to subsonic, and then it presses up against that obstacle. And on the day side of the Earth, this means it's going to compress the Earth's magnetic field on the day side, stretch it out to a nice long tail on the night side, and give you this, this wonderful looking magnetospheric shape. Now, if, as I show here, or as the graphic I stole from NASA's webpage shows here, the interplanetary field is oppositely aligned with the Earth's field, the process of magnetic reconnection can begin. And this is the process by which fields of opposite polarity can merge together to create new field lines of a different geometry. Now, at the dayside magnetosphere, this means taking a purely solar wind magnetic field line, a field line that is closed to the Earth at both ends, and merging them together to give you an open line, one that is connected at the Earth at one end and goes out to the solar wind flow on the other. The solar wind continues to drag these field lines back onto the night side, effectively stripping magnetic flux from the day, packing it onto the night side. You squeeze those field lines back together on the night side, and reconnection can happen again, turn open field lines back into closed lines that advect forward and replenish the flux on the night side, or on the day side, excuse me. So this process is known as magnetospheric convection, and it's now widely accepted as the main way in which the solar wind delivers energy to the magnetosphere system. Now, back in the early days of space exploration, satellites did not have composition measurements on them, so scientists saw hot, tenuous plasma in the plasma sheet and the ring current. This kind of reminded them of the solar wind, and so they constructed a model to describe how solar wind could enter the magnetosphere and populate these regions. And it follows the same logic as magnetospheric convection. The flux tubes that are full of solar wind plasma, oh, this is my animation comes back, there we go, advect through, they reconnect, and those flux tubes are reconnected to the night side, allowing solar wind plasma to enter the plasma sheet. It's injected earthward and energized to become part of the different populations. Now, ionospheric people knew that there was a second potential source of plasma here that we were ignoring, and that was the ionosphere. If you think about a flux tube connected to the Earth, the pressure gradient from the ionosphere to space, obviously, is strong enough that you'd expect some thermal escape of that ionospheric material into space. This is especially true on open field lines, where it doesn't matter how much material flows out, it's going out into interplanetary space, and you can never reduce that pressure gradient strongly. Because the electrons are light and mobile and fast, they're able to escape a little faster. You get charge separation, and an ambipolar electric field forms between electrons and their much heavier ion counterparts. And just in case you were wondering, this is not to scale. So this electric field follows the electron pressure gradient, and while it does indeed retard the escape of the electrons, it's very effective at helping to pull the heavier ions out into space. And so this is one of the mechanisms that was recognized very early that could help lower the escape potential of heavy ions and get them out into space. If you do the math here and you include gravity, you realize that a Laval nozzle situation forms, just like on the sun. You have a retarding force, you have an escape force. Depending on the balance of those two, you might get a slow subsonic flow, or you may get things accelerated supersonically, creating a solar wind, as in the case with the sun, or a polar wind, as in the case at Earth. And so this was one of the early questions in space, is there a polar breeze, is just allowing kind of this slow escape of ionospheric material into the magnetosphere, or is it a true polar wind that is blowing out material supersonically and acting as a strong source of plasma to the magnetosphere? So early on, with measurements of the plasmasphere, which is that cold, dense, co-rotating population, the general consensus was that the plasmasphere was just an extension of the atmosphere, and it really had nothing to do with magnetospheric dynamics. And the really exciting populations, the plasma sheet, the radiation belt, those were still solar wind. And in the early 70s, this was turned on its head by measurements presented by Ed Shelley in 1972, where using a instrument capable of seeing composition, saw large amounts of warm, even hot, so KeV type, oxygen in the plasma sheet and the ring current. This is problematic for two reasons. One, there's not a lot of oxygen in the solar wind, not nearly enough to account for these measurements. And two, it's warm. It's not the cold plasmasphere that everybody had grown to know and love. And so this kind of suggested that, one, there is a polar wind providing a lot of plasma, and two, it was entering the plasma sheet, being energized and playing a role in the region where the solar wind was thought to be the dominant population. So later, this was eventually, I don't want to say put to rest, but the Dynamics Explorer satellite with the RIMS instrument flew over the pole and was able to confirm the existence of a supersonic polar wind outflow. And the subsequent studies with this instrument and others led Rick Chappell in the mid-'80s to suggest, hey, there's so much ionospheric mass entering the magnetosphere that it could account for not some, but almost all of the plasma we are seeing in the magnetosphere. And with that paper, Rick gave us this paradigm of plasma entry into the magnetosphere. Instead of a solar wind-driven system, we see plasma entering on open field lines, advecting back and being deposited at different areas into the plasma sheet where it can be injected and play the role of the ring current and plasma sheet population. I'm a little biased. I would say that Rick was, for the most part, strongly vindicated by subsequent observations, for example, from Polar Tide. The cluster mission has been incredibly successful at showing the importance of ionospheric plasma in the magnetosphere. I'm not going to blow this picture up, but I have to speak to it because it's just so neat. One of the things that's extremely challenging to do in the magnetosphere is detect the so-called invisible population. This is a very cold plasma, only a few EV, and if your satellite has even a small amount of a positive charge, it's completely shielded and you cannot detect this population. Engvall and his group, there's a whole bunch of people working on this, are investigating the electric field in the wake of the plasma wake in the satellite, and from that they are able to infer the cold plasma density. And this picture, if I blow it up, it's a little bit of statistics of when they did and didn't see this cold population. And what's really exciting here is they found it is more difficult to find a period where they don't see this population than times when they do. The ionosphere is always pumping out material. It's always acting as a strong source. So these kinds of studies put together allow us to develop plots like this. This is cluster, and I can't remember the instrument. It's the electric field here. So 1 second. Can you guys hear me okay, by the way? I'm very loud. This allows us to make plots like this, and this is from a paper by Nose in 2004. And what we're looking at here is the energy density ratio in the ring current and the plasma sheet between oxygen and hydrogen in red and helium and hydrogen in blue as a function of storm strength, characterized by DST. And what we see here is that heavy ions like oxygen can become the dominant pressure-carrying population the stronger the storm gets. So now we've taken this paradigm of the solar wind being very important for plasma sheet and ring current development, and we're completely changing that and looking now at the ionosphere as the critical source. And this is a picture, I believe this is from, where did I steal this one from? I think this is again from one of Rick Chappell's paper, who he really pursued this line of work. Kind of again reworking our paradigm such that we can look at the regions in which the ionosphere is an important player in mass. And of course you have over the poles, the plasmasphere, the cold population in the lobes, and the plasma sheet and the ring current, and what Rick calls the warm plasma cloak. So this is 10 eV to 3 keV particles wrapping around the Earth. So simultaneously with this observational work, ionospheric people were learning more about how ionospheric outflow, how particles in the ionosphere are energized and enter the system. And we've moved from this very simple classical polar wind picture where we're focusing on ambipolar electric field to a much more complicated picture where we're talking about centrifugal acceleration, where plasma on a flux tube is whipped up along the flux tube as the magnetic field is pulled over the poles, or transverse acceleration of heavier ions due to electromagnetic waves that increases the efficiency of the magnetic mirror force blowing stuff out. And so you get this very complicated picture of all these processes that, in my mind, demonstrates that Bob Shunk was clearly able to prove it doesn't matter if your picture is really simple and cartoony. If it's useful, it's going to get a lot of use. So I'm sure everyone's seen this picture about 20 times now. So you think with this growing body of evidence that global modelers would be excited and lining up to find new ways to accurately add this source to their models. The opposite of that is true. It was not until the very late 90s that the first paper came out in terms of global fluid models, talking about including this source in a self-consistent way. And that was with Bob Wingley and his group at Washington State, and they had a very simple plasma source for hydrogen and oxygen in their code, but even with that simple source, they saw a lot of interesting features. It wasn't until almost 10 years later that we saw a broader that we saw a broader acceptance of this kind of inclusion of ionospheric outflow in global models. It really started with my graduate student office mate, Alex Glosser, developing the polar wind outflow model and incorporating it into BATS R Us, both single fluid and then subsequently multi-fluid. This was particularly exciting because at the time I was working on data model validation of BATS R Us, and including polar wind improved the data model comparison so much that we thought we broke the code. It was both drastic and a little scary. Right around the same time, the SISM group found a different way to include causal outflow in their code, and one that's very, very interesting. They calculate the precipitating alphanic flux heading towards the inner boundary of their code, and they use the empirical formulation developed by Bob Strangeway to convert that to outflowing oxygen flux. And Oliver Brambles, Mike Wiltberger, Bill Lotko, those guys have a series of very interesting papers and presentations using that. For my own part, I worked with Aaron Ridley to try to see what the balance was between ionospheric plasma and solar wind plasma in BATS R Us. And this really started as a project that was an exercise of frustration. I was very upset that I couldn't get more solar wind plasma into the BATS R Us simulations. It seemed to all come from the inner boundary. And it was Aaron who said, maybe that's the right answer, Dan. Later, while working with Vanya and Soren Zaharia at Los Alamos, we took Alex's model, incorporated it with BATS R Us and a ring current model to see how outflow affected the development of the plasma sheet and eventually the ring current. Now, one theme you see as you move from this end of the timeline to this one is that modelers, since kind of catching on to this idea of ionospheric outflow, have worked very hard to find ways to include causal outflow. So outflow that is not a simple static source, but is dictated by the dynamics in the magnetosphere to some degree. And when you do that, it really opens up a whole new set of interesting results. And I think probably the biggest one so far has to be the work of Oliver Brambles that was published in Science. They used the LFM causal outflow with the Strangeway relationship and looked at idealized but very strong driving events. And when they did this, the initial burst of oxygen outflow would enter the plasma sheet in the ring current. It would mass load the tail to such an extent that a plasmoid would form and break off. And the field lines earthward of that X line would dipolarize, release another set of electromagnetic waves, which would in turn be converted to outflowing oxygen flux. And so long as you continued to drive the system strongly from the solar wind, this process would repeat ad nauseum. And the net result of this, which is extraordinarily exciting if you're a magnetosphere person, is the development of global sawtooth oscillations, which is one of the outstanding mysteries in magnetospheric physics. What was really exciting about this result was it was the first time in a global MHD code we were able to get a sawtooth oscillation without doing something really tricky to the reconnection rates in the tail to keep them going forever. Furthermore, what we're looking at here is the periodicity and the magnetic inclination angle in the tail. Oliver found that if you tweak the parameters that were feeding the Strangeway relationship, you could control the period of the sawtooth event. This is extraordinarily exciting if you're a magnetosphere person, being able to not only finally get your model to do this, but being able to control it with the outflow parameters. So over these several decades, especially in modeling, we've moved from a paradigm of the solar wind being the only player in town to the ionosphere playing a critical role. And furthermore, the work of Oliver Brambles, I think, really demonstrates that you can't treat this as a static one-way source. You have to include it as an integral part of the nonlinear magnetosphere-ionosphere system. And so when I saw his results, so this is, excuse me. Yeah, so these are the solar wind parameters he used to drive this. So there's a lot going on in this plot. I'm so sorry. If you look at his the auxiliary material in the actual paper, he has a pretty descriptive table saying what were the parameters for the strange wave, what were the solar wind parameters, and things like that. And the kind of quiet time speed is about 400 kilometers per second. What? Oh, polar. I'm sorry. I thought you said solar. Yeah. Boy, you say 10 kilometers per second? Yeah, it's. I think there's a lot of variation in there too. Between it depends on the energization mechanism. Yeah. Yeah, and I want to say with the Bramble study, they went, and you guys are going to be able to know more about this than I do, they went as high as like 50 kilometers per second because they're trying to represent a more energetic portion of it. Yeah. 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 Yeah, I'm 400 kilometers. It comes out there really fast. Yeah, that's really that's the review paper for ionospheric outflow. Okay, so as I was saying, Brambles, it was really all about this magnetotail ionospheric outflow feedback loop. And so I proposed the question, are there other regions in the magnetosphere where you can see this dynamic develop? Now at the time, I was working with Vanya doing ring current stuff. And so I thought, what about the ring current? As I said before, the ring current is warm to hot, KeV type plasma. It's the pressure carrying population. It is really in charge of controlling geometry of the magnetic field inside the inner magnetosphere, depending on its strength. And we, in terms of attaching it, trying to establish this chain of events between the ionosphere and the ring current, there are already several links in place. We know that the ring current is fed, in terms of mass, quite strongly by the ionosphere. So there's our first link in the chain. We know that the ring current pressure gradients drive region 2 field-aligned currents. These are lower latitude currents that close through the ionosphere. So we're going to link, now we have another link in our causal chain. If only we could somehow connect field-aligned currents to outflow. That's convenient. Tomas Gambosi and Andy Nagy in the late 80s were able to show how field-aligned currents can be very important here. They had a very simple ionospheric outflow model. It was 1D, so they were solving the equations of motion along a single field line. And they did this typical shortcut of, instead of solving for the electron momentum equation, they're going to get electron velocity such that, given a current density along your flux tube and balancing it with the total ion flow, you know what your electron velocity has to be. They then set up a situation where they reached an equilibrium solution and then changed the current density, either upward or downward. And when they had a upward current, the electrons are coming down, and they found that the electrons would compress at the bottom of the code, heat, increase the radial electron pressure gradient, and therefore increase the ambipolar electric field. The impact on the ions was such. What we're looking at is flux with 0 being in the middle, so upward on the right side, downward on the left side, versus altitude at several 5-minute steps from when the current was turned on. The dotted line, is hydrogen flux. The dashed line is oxygen flux. And with this sudden surge in ambipolar electric field, it caused a sudden increase in oxygen outflow that would eventually return to a new equilibrium state. So this is kind of the final link in our puzzle here. Logically, we can see all the steps required to connect outflow to the ring current back to ionospheric outflow. We just want to put together a bunch of tools to see if it really does anything. So these are the tools we're using, a whole bunch of models. We're going to start with, Bats R Us. which stands for the Block Adaptive Tree Solar Wind Row Type Upwind Scheme. I think you're not allowed to graduate from Michigan unless you know that. It's a global magnetohydrodynamic model. The advantages of these is that it gets the whole system and you only need a few inputs, the big one being the upstream solar wind conditions, and you can drive self-consistently more or less a lot of the system. We're going to be using multi-species MHD, and this is a convenient shortcut. With multi-fluid, you're solving as many sets of the continuity, momentum, and energy equation as you have species. So you can have counter-streaming flows and all these other effects. But if you're not too worried about that and you want your run to go a little faster, as sometimes impatient postdocs want to do, you can go ahead and turn on multi-species MHD. So this is essentially single fluid. However, we have several continuity equations so that each numerical cell knows how much of the fluid is species A versus species B. And as it turns out, in a macro scale, it doesn't make a big difference compared to multi-fluid typically, depending on what you're looking at. As is common, we run this with a height-integrated ionospheric electrodynamic solver. The unofficial name is the Ridley Ionosphere model, or RIM. And essentially what we're doing is, given the field line currents calculated by BATS-RS and some sort of ionospheric conductance, calculating the horizontal currents and the electric potential. For the Ridley model, the conductance is a empirical model based on a whole lot of AMI runs. AMI is the assimilative mapping of ionospheric electrodynamics. There are a lot of acronyms in space science. It's a little ridiculous. It takes a lot of data from magnetometers and in situ measurements, inverts it to give you a global view of ionospheric electrodynamics. Aaron used many, many years of AMI results to get conductance as a function of local current density, and that has worked very, very well in BATS-RS. Next is the polar wind outflow model. So this is the same thing, essentially, as the Gambosi and Nagy model, but now with many, many, many flux tubes. Also, instead of just doing radial motion, we get horizontal motion by letting all those flux tubes advect with the local E cross B speed. This is very similar to some of the earlier Schunk models before they started incorporating the particle and cell portions of it. Again, the key input here is current density. It helps set the topside heat flux and the current density. The next model we're going to do is kind of two models in one. It's Los Alamos's RAM-SCB, which stands for the ring current atmospheres interaction model with self-consistent magnetic field. And so what this is Vanya, the RAM model, originally developed by Kozira, Jordanova, H. Falk, Mike Lamone, but now coupled, this is a bounced average drift model, kind of a typical ring current model, 1.75 to 6.75 RE, several ion species. But now coupled with Soren Zaharia's self-consistent magnetic field model. So what we do here is we have some initial magnetic field, we take the anisotropic pressure from RAM, and we use that to reach a new force balance equilibrium with our initial field, such that we're allowing these particles to drift magnetically self-consistently through the SCB field. Now, we want all these codes to work together as a unified system and not as a bunch of disparate parts. To do that, we're going to use the Space Weather Modeling Framework. I'm going to release a glossary after the talk. And what this code does, by itself, the framework really doesn't do anything. But when you take some otherwise disparate codes and start plugging them in to spots where they're applicable, for example, finding a radiation code and a radiation belt code and plugging it into the radiation code port and one for the ring current and all that, the framework will take all those codes, execute them, synchronize them, and couple them together. And so this is the coupling scheme we're using for these simulations. So BATS-RS is going to hand field line currents to the polar wind outflow model and also the RIM. RIM is going to give electric field to RAM-SCB and PWAM, and it's going to use that to set the tangential inner boundary conditions, velocity inner boundary conditions for BATS-RS. And the outflowing plasma from PWAM at the top of the PWAM model is going to be used to set the inner boundary mass and radial velocity conditions of bats R Us, effectively driving outflow into this model, which can flow and feed the outer boundary of RAM-SCB. Now, the situation I just described is a one-way coupling scheme with respect to the ring current. All these models are working together to feed the ring current, but we are not allowing the ring current to push back. How do we do that? It's all about pressure coupling, and this is a very common thing to do now. MHD by itself is notoriously bad at giving us realistic pressure distributions in the inner magnetosphere. So what we do, we have a dedicated ring current model, and we allow the pressure distribution here to nudge that of bats R Us with some time constant to improve the inner magnetosphere pressure profile in bats R Us. This is going to drive region 2 field line currents in RIM, which is going to affect PWAM, and we should see all these things working together. So using this setup, we're going to look at the August 31st, 2005 storm. I'm doing a whole lot of simulations right now. I cannot keep any of the dates in my head straight. This is a very nice storm. It's moderate, DST of negative 120, but it's got an excellent period of about 6 hours of strongly southward negative 15 nanotesla IMFBZ. So this is the orientation you want if you're going to effectively drive energy coupling between the solar wind and the magnetosphere. We're going to simulate this one-way coupled with the ring current, and then two-way, activate this pressure coupling, and try to investigate if we can establish this nonlinear feedback. So let's start by making sure our coupling works. This is the equatorial pressure profile in bats. In RAM-SCB, the sun is at the top, so dawn, dusk, midnight. And down here, once I start this, we see in green the dynamic pressure of the solar wind, and in blue the IMFBZ. So we can watch this progress. And oops. Oh, come on, PowerPoint. There we go. And immediately, oh, you can barely see it in this color on this projector, but there he goes. So you do see it's successfully nudging the pressure in bats R Us to look like that of RAM-SCB. Now, certainly there's some smearing here. It's not nearly as sharp. We're talking about a rectangular grid versus a cylindrical or cylindrical grid here. So we certainly expect this to be not quite as sharp, and the resolution is higher here. But overall, pretty good. We saw the asymmetric ring current form in both, and then symmetrize towards the end of the storm. Perfect. This kind of stuff is not new at all. There are a lot of codes that couple ring current models with MHD, and these are the kinds of results you expect. These are the radial currents coming out of bats R Us to RIM. Yellow to red is upward current, blue is downward. This is one-way coupling, this is two-way coupling, and we're looking at 4 points during the storm. This is pre-storm, where our current distribution patterns look very similar. This is early main phase, late main phase, and very early recovery. Here, looks the same, not a big deal. Here, the ring current's starting to build up, and we see, compared to the one-way case, our two-way coupled case is seeing stronger field line currents. The peak is moving from the night side over to the pre-dusk sector with a little bit post-dusk. A broader and more strong upward current on the dawn side. We see a post-midnight peak here, and this pattern only gets more obvious as you move on in the storm. The peaks of the current move, the peaks of the current become stronger throughout the whole event. I didn't show this here. It tends to, there's a little bit of a difference here. Oh, no, it's region 1 and region 2. It's all of them, yeah. Sorry. I'm so focused on the region 2 that I forget the other ones exist. But to the question I imagine you asked, including the ring current tends to stretch out the field in the inner magnetosphere, and so we do get some location differences in the region 1 as well. Well, I'm very glad I asked it. As I was saying, we did some comparisons with the results of the Weimer model. So this is an empirical model based on, oh my gosh, is Weimer DE or is it DMSP? DE. Oh my gosh, I can't remember that, and I just wrote it in the paper. And what we found was that the result, it really, including this kind of coupling, and again, this is not unexpected whatsoever, really improves the region 2 field line currents compared to the Weimer model, which is very well validated. So we're very happy with this. So now what we want to see is how is this affecting outflow? We're really hoping to see a difference in oxygen outflow. A problem comes to mind, however, that, you know, in the Pelosi and Nagy results, the oxygen fluxes were transient. Once the current changed, you saw a burst of oxygen and then it reached a new equilibrium. And these guys are more or less relatively stable, but we get a big help from the convection of the field lines. So you can imagine a field line flowing through here and then into this region of upward current. And that is going, the flux tube, in the flux tube's frame, you see, okay, not a lot of current. Oh, whoa, there's a big burst of upward, and then it moves out of it and it relaxes back to normal. So it can never reach that equilibrium state. So we hope to see a big difference in flux. And of course, I wouldn't be presenting this if we didn't. What we're looking at here is oxygen flux from the top of the polar wind outflow model at the same times I showed in the previous slide. The scale here is 10 to the third to 10 to the fifth, one-way, two-way coupled, and exactly where we would expect, we're seeing this increased outflow. So for example, here, early storm, there is a stronger upward field line current in this sector. There's our oxygen. It is stronger here. I suspect that's because we're moving from a region of now downward field line current here, which cools the electrons. They are flowing up, they spread out, they adiabatically cool, and so the change in ambipolar field is much more drastic from this new equilibrium to when you then crunch it down again. So we are seeing increased activity up here compared to the one-way coupled runs. To quantify this effect, let's look at fluence. We're going to integrate the flux over the entire polar cap to get one number for every time. This is on a log scale, 10 to the 23rd to 10 to the 25th. 10 to the 25th is kind of the golden number when it comes to observations. Studies trying to get at a fluence number usually fall in that 10 to the 25th ballpark. We're looking here at net fluence, so the fluence of all ions. One way, for the rest of the talk, one way is going to be solid lines, two way is going to be dashed, and eventually these two split off, and there's about a factor of 2 difference. Now, based on the Gambosi and Nagy results, you would expect this to not manifest strongly in the hydrogen fluence, and indeed there's a little difference, but it's very similar. So this means the difference between these two black lines must manifest almost entirely in oxygen, and there it is. Towards the end of the storm, we're looking at a difference of 6 times in fluence. So this is a significant amount of additional oxygen outflow that we're getting from this two-way coupling. So at this point, we've kind of marched through our train of thought here. We started with the ring current, we followed it to the ionosphere, and we looked at the effects of the ionosphere. We want to see if this additional outflow is changing the magnetosphere results. And we're going to look at that in terms of percent oxygen by number through the length of the storm. This is the one-way coupled run, this is the two-way coupled run, and we're looking at the noon midnight meridian, so the side of the magnetosphere. And the darker green, the more oxygen we're seeing. Like the other results, it starts off very similar, no surprise there, but as we go, we start to see these lower latitude night side bursts of outflow in the two-way coupling run, and this eventually really starts to differentiate itself from the one-way coupled run. And if I can show you a little more clearly, this is early storm main phase, one-way, two-way. Early in the storm, it's these mid-latitude bursts of outflow that are populating the near ring current plasma sheet, so between 10 and 15. And you just didn't get those without the two-way coupling. I would have to look what it's at coming out of Plum. I would have to look up the numbers for both. Typically in Bats R Us, you can get easily, once you're here, 10 keV is pretty typical for a storm in Bats R Us. With multi-fluid, completely different talk, but with multi-fluid, this is one of the places where multi-fluid really matters. When you have oxygen coming back here at this point in the tail, you get a little adiabatic heating before it hits the ring current. If you have oxygen coming out of here, you have a lot of adiabatic heating before it hits the ring current. We have 2 and 3 fluid models where you see all of this just pop up clear as day in the Bats R Us results. It's exciting stuff. Excuse me, later in the run, again, it's just the amount of oxygen leaving the cusp and polar cap is stronger and broader than the one-way simulation, and these mid-latitude, excuse me, I shouldn't say mid, it's still pretty high because it maps down to a high latitude spot, but lower than your typical polar cap region. Jets are still stronger than what you're seeing with the one-way coupled ring. So our last step in our chain here is to return to the ring current. And we can summarize the effect on the ring current by looking at the average energy density per species in RAM-SCB. Again, the solid lines up here are for one-way coupling, the dashed lines are for two-way coupling, and we see some very interesting dynamics here, but the takeaway message is with one-way coupling, we saw a hydrogen-dominated ring current where the oxygen took a long time to catch up. With the two-way coupling, the oxygen surpasses the typical pressure, typical energy density of the hydrogen sooner, and it elevates to dominate the ring current dynamics. So we've followed our whole chain of command here from the ring current to the ionosphere to outflow to the magnetosphere and back to the ring current again. And we see how these two are playing off each other quite clearly. Maybe not as dramatic as the tail with the Sawteeth case, but it's still there. Now, I want to emphasize that I consider these results really a proof of concept study, and there's a lot of room for improvement. We really only focused on more of the classical polar wind. If we include more energetic sources or different energization mechanisms in our polar wind, would it perhaps lower the impact that this effect is having? Probably. I'm really not happy with the timing issues we saw on the previous slide. It seems to take a long time for this feedback loop to build up and create a big difference in the ring current. We're looking at really late storm compared to mid-storm. And so this, to me, speaks to the need to perhaps have a longer preconditioning phase when we're doing the simulation, both for the polar wind and the magnetosphere. One of the things Bill Peterson loves to talk about is plasma in the pipes. Mass loading the magnetospheric lobes such that the ionospheric plasma, when you turn on the magnetospheric convection, just connects the pipes from the ionosphere to the magnetosphere directly to the plasma sheet, and it already is preconditioned to have a lot of mass there and give you a faster response. And I think that's something we probably need to look into. We did some comparisons to observed values here. The DST really reflected what we saw in terms of the pressure distributions, where the early response of the storm is not where we want it to be in terms of having a realistic model. But we are improving the overall comparison with this additional pressure. It's pushing the MHD DST from maybe -10 nanotesla to -150, down where we want it to be. So it's certainly helping later. And our total fluence and flux numbers are a little low overall, and to me this speaks to the need of including more energization mechanisms in our polar wind. However, the takeaway message that I think is valuable here is that when we're looking at ionospheric outflow, we should treat it the same way we treat ionospheric electrodynamics. It's not an input to the magnetosphere. It really is an integral part to the ionosphere-magnetosphere system, and you get all these nonlinear mechanics when you include these different connections. So that's all I have. If you have any questions, I'm happy to answer.
event that you were focusing on had a really high solar wind density to begin with,
Yeah.
not just VZ southward.
Let's pretend that was slide 15. Oh, so close.
Okay, so the question is, have you done a lot of other events, and do you think that there's an effect on this whole result that you're showing that might be different if you had density not going so high? It does change your geometry of the magnetosphere.
Yeah. When you first asked that question, before you said geometry of the magnetosphere, well, you're changing my answer as I go. Let me give you a quickie primer on what happens in Bats R Us. In Bats R Us, the plasma sources are solar wind and the inner boundary, which is a proxy for the ionosphere, and how well of a proxy that is depends on what you're setting it to. Are you using a PWAM? Are you using something simple? But essentially, especially with single fluid, when you have northward IMF, you get reverse convection that really effectively and strongly is able to draw in the solar wind plasma, and it creates the cold, dense plasma sheet. And that is something that's really important for preconditioning storms in Bats R Us. Now, when you turn southward, my rant here is completely 100% valid. For southward IMF, the dominant plasma source in Bats R Us is the ionosphere for the central plasma sheet and the ring current. You do get flank entry, and this is kind of a contentious thing depending on who you're talking to, but in Bats R Us, you do get flank entry of solar wind material, and the solar wind pressure, you get these kind of vortices forming on the side. If the pressure's strong enough, it will push those until it impinges on the central plasma sheet, and that can cause things. We've been doing this with 3 fluids now: a dedicated solar wind fluid, a dedicated oxygen fluid, and a dedicated hydrogen fluid. And there you will get, for southward IMF, some over the pole entry of solar wind plasma, but it's still absolutely a minor species. Those are the things I really think about here. I think if we had less pressure, it probably wouldn't change this result drastically.
In the movie, can you go back to that where you had the flow with the green
blobs?
Yeah, the green blobs.
You know that you can type any number in PowerPoint and go directly to that slide, which makes for some really fun guessing games as to where you left your slides at. It wasn't 25.
There we go.
That. Yeah.
Yeah, I see that you have, say, the 6 hours of kind of steady southward IMF, and it seems to take a while to get going. But once you get going, then it looks like there's a lot of oscillation. Is that oscillation, do you know if that's just inherent in the system, or is that solar wind driven?
I think that is a function of solar wind. Oh, let's see. Let's pretend it was slide 15. No, it was not slide 15. Let's pretend it was slide 20. Oh, that's cheating. Come on. Let's be serious here. Part of the storm is a lot of IMF-BY variation, especially in that back half of that storm. I was wondering about that.
Yeah.
And in a paper with Vanya and the gang, Alamos, we looked at what this means for the tail, and you see your oxygen in the tail shift from side to side and do different things. And we have these local time, universal time maps of that, and it's pretty cool.
Back to the blob movie toward the end.
Sure.
The latitude distribution of the oxygen outflow, yeah, that plot's just fine.
Sure.
The lower latitude stuff looks like it's in the plasma pause. Is that the plasmasphere that's filling in the inner magnetosphere?
What quadrant? Guy?
Yeah. Plasmasphere?
Here?
Yeah. Or would you call that auroral field lines?
These are probably auroral field lines because they're mapping down to a higher latitude. The plasmasphere is a squishy thing in ideal MHD, right?
Right.
So
you're pushing every limit here in this modeling. That's cool.
So I'm very hesitant to say it's a plasmasphere. Joe Borofsky used Bats R Us in one of his papers and kind of accidentally created a plasmasphere with a ugly looking plume and saw that it really messed up the day-side reconnection dynamics. But I would be very hesitant to say that's anything that resembles an actual plasmasphere.
That probably is.
Questions in the back?
So on the same slide, in the fourth quadrant, in the two-way coupled simulation, it not only looks like you have lots more oxygen coming from the subaurora region, but you also have a lot more coming from the cusp. How is the ring current coupling affecting the cusp?
Let's pretend it was slide. Let's just go back. I'm done playing that game. You know, when I was doing that company thing, there was a guy from the business school. Damn, he was on it. And he taught me this trick, but every talk we went to, where we were talking to people who actually had money to give us, he had a list of every slide number in every slide. And people from the audience would say, well, what about this? And he would just hit the button without hesitating, and bam, it would pop up, and people would be like, oh, well, this guy is on it. Okay, no, that's a really good point. This is what I strongly suspect, and I need to break down further. We're working on a follow-up paper to really look at the details of what's happening in Plum. And what I suspect is that field lines going through this region, in the one-way couple, they first see an upward current that's going to cool the electron fluid. And I'm sorry, the blue is downward current. Thank you. Yes, thank you. Is going to cool the electrons, give you a very small ambipolar field. The system is going to try to quickly adjust to that new equilibrium. In the picture I showed you from Gambosi and Nagy, that started to happen, with tens of minutes. And then all of a sudden it's going to pass through the upward current with the downward electrons. Yes. So what I suspect is happening here is that you have stronger downward currents. So if that guy, your flux tube's passing here and then here, I suspect the equilibrium you're trying to develop here is very cool, very weak ambipolar electric field, and then the change is very drastic. So the flux tube thinks, instead of having, let's say, I don't know what let's pretend this number is 10. I can't remember what it is. I think this is microamps per cubic meter, squared meter. Rather than going from 0 to 10, it's going from negative 10 to 10. And so the change is much more drastic. And in Gambosi and Nagy, the strength of the transient was dependent on the strength of the current transient. We're, like I said, breaking that down now.
Yeah, so on this slide here, the 1430 time frame, there doesn't look like there's that much difference in this instantaneous snapshot between the field-aligned current patterns, especially even the region 2 current patterns seem to be pretty strong, versus the striking difference that you see on slide 26, since I've memorized your slide numbers, or even right there, of the outflow.
Slide 24.
Yeah, but the green one was, you could see it as well with the high latitude regions there.
Question.
So is it a time history effect that you're seeing integrated over time that you've got a slight difference, or is it really more of an instantaneous thing? I'm just trying to understand the dynamics.
I think there's a little more work to give you a definitive answer. But to defend this plot a little, here we're very close to 0. Here we're another, I can't remember what the separation of the contours are. This is the problem of making plots long before you talk about them again. So yeah, we are moving the peak current over here and increasing the peak. Here also, for some reason the region 1 currents are stronger.
That's something we see in LFM RCM simulations. When we get the region 2 currents in there, we see a proportionate increase in the region 1 and region 2 currents when we're doing the coupling.
That's always the case with BATS RS. For example, here I think this is more of a geometry difference. These two are very, very similar. I could speculate, but
I guess it'd be interesting to look at a percent difference kind of plot or something.
Right,
Roger.
yeah. To me, the 18 UT looks like the region 2 are much stronger.
Yes. And remember that this is, well, yeah, this is where, I mean, this one is also extraordinarily drastic, especially on the night side. So maybe I picked a bad time here.
And it's late in the storm when you see the most outflow anyway.
Outflow,
so.
Yeah. Oh, we got one back there. I'm not the holder of the mic.
So I have a somewhat naive, more general question. You showed summarized the comparison with observations, and if I understood you correctly, then your major concern was whether what you call preconditioning of pre-storm of your model, which is basically how realistic your data assimilation is of the whole scenario, affecting how close you come to what sort of one would really observe. So my question then is, so is it that is the biggest gap now, the data assimilation problem, or is there missing physics still in these models?
Yes.
And what are the most striking pieces of missing physics that you would be worried about?
Oh Lord. Let me start with the first part. That the preconditioning I'm most concerned about is mass preconditioning of the magnetosphere. The polar wind, as Bob Shunk likes to say in his Bronx accent, goes 24/7, 365 days a year. And so, but we're only starting our code in our magnetosphere and our outflow code a few hours before the storm. So it would be, and I've done some preliminary studies on this, it would be better to start the storm even as much as a day earlier to allow the slow, cold outflow to really saturate slow-moving flux tubes, and then when we turn southward. Bill Peterson came to my poster a long time ago and gave me a hard time about the pipes, and I did a simulation, and he was probably a little more right than I cared to admit. Your second question, that is very difficult. For me, and here's me being extraordinarily obvious, or honest to a crowd here. Reconnection physics in ideal MHD is a huge question mark. What's driving reconnection here is numerical diffusion. It is a product of the discretization of the equations that we're using. It's something you impose to gain stability in your numerical scheme. It changes with local wave speed and grid resolution and time step. We are very lucky that global MHD codes give us pretty darn good answers for not having very good reconnection physics. And to me, I think that is something that should be worked on more. And I think we're doing some interesting things at Michigan, but that's another story.
So to compare to data, go to 24, and those snapshots of ion outflow in the magnetic local time distribution don't look at all like the average magnetic local time distributions that exist. So one of the tricks that Brambles and his co-workers did was average outflow over the whole interval. If you were to take and average all of those outflow things and say you were taking a statistical thing, what kind of an outflow distribution would you see? Would it look more like what I would like to, what we see on average observationally is 30% of it is at noon, 30% of it's in the 2100 MLT distribution. Not very little in that.
Oh, sorry, yeah, I'm over here.
It's at noon, which should be at the top, and at 1900, which would be at lower left on average. That would be a fun thing to do. And if you did it, you should publish it. And if you didn't, you should forget it.
Those are good points. essentially, it's being driven by the field line currents, which are, I showed that slide several times. I can bring it back if you'd like. And the flux tubes advecting with the local E cross B speed in and out of those field line current regions. And that convection pattern is very dynamic, especially for this simulation. You could imagine it, a very simple southward convection looks like two cells, other way around here, like this. But we have a strong BY component. It's twisting it, it's contorting it. There's a lot of things happening.
Questions? Well, if there's no more questions, before we leave, I want to hand this to Yu-Hong. She wants to make some announcement.
New arrivals of HAO. One is the new advanced study program postdoc, Anna Melamushenko. She's sitting on the second floor of HAO next to Roger's office. And then the other is Jessica, a graduate student from University of Torino in Italy. She'll be here for a month working with Sarah Gibson. So just
Thank you. Let's thank Dan again.
Thank you guys very much.